we are on to our next talk of this session. Vitaly Feldman, who as we see in his thing, he's currently an Apple privacy researcher, but he has also previously been a Google researcher, and he visits Simon's a lot. He does tons of amazing work in the privacy machine learning space, and he will talk today about kind of memorization and if it's a good or bad thing, I guess. We will learn.
Thank you, Rachel. And it's always great to be back at Simon's. Some of this work has actually been done rather with Simon's. And part of this work were done with my collaborator, Qian Zhang, who is at Google Research. This work, the basic theme of this work, the basic question we address in this work is kind of fundamental question of the role of memorization and generalization and learning more generally, but it does have some strong motivation and connections to privacy, and also gives some insights to phenomena such as disparate effects of learning techniques that learning techniques have on the accuracy on different subgroups in the data, which might be relevant to the themes of this workshop. Anyway, so as I mentioned, we'll be trying to understand the role of memorization. And the starting point of this work is this sort of well-known observation that state-of-the-art deep learning networks tend to fit the training data very well, even when the test error or their actual accuracy is not that high. For example, a typical training set error is often close to 0 or 0, whereas test error could be anywhere between 10 and 30%. And what that implies is that in a way, the training algorithm memorizes these training labels that it cannot predict well, or in a way, one can think of it it seems to overfit to the training data, even though these are some of the best algorithms. And the reason this is somewhat surprising is that we typically learn in machine learning courses that machine learning algorithms are supposed to balance some kind of notion of capacity with the fit to the data, so as to not to overfit. So overfitting or memorizing a lot of data should be bad. So by now we have a lot of sort of much better empirical understanding of this phenomena, thanks to the sort of pioneering work of my collaborator Zhang and his colleagues, who, for example, show that standard learning algorithms, when you feed them a completely randomly labeled training set with million examples, ImageNet, will achieve training error of just 9%, which is very low, even though the test error, it's completely random labels, will be close to 100. Yes.
Training versus test.
Yes.
Training test is in afterwards, yes?
Yes, test is afterwards measured on the test set, which is our proxy for the true error on the population. And training is just the empirical error.
You're not saying that the test error is essentially you're wrong on everything.
Yes, yes.
You are saying that.
In this example, you're fed completely random labels. So there is no hope you will actually learn anything because you're fed a data set which is kind of useless.
So what does it mean that the training error is 9%?
Training error means 9%. That training error is how well you predict the set you were trained on, the empirical error. So when you feed the data set, the learning algorithm actually outputs a model which predicts correctly on the training data, that it was given. Almost all of them are predicted correctly. So it kind of fits the data that was given, but doesn't fit the data it hasn't seen, of course. So the authors of this work also point out that this is a phenomenon that is not well explained by existing theory of machine learning. So, and the goal of this work is to give an understanding of why do we see this memorization? Why does all this happen? But before I can explain, let me define memorization more formally. And for this purpose, for the purpose of this talk, memorization will intuitively capture the notion we say that an example in a data set is memorized if this example is fit by the model that when it receives it in a data set will accurately fit the label on that example. But if you were to remove that example from the data set, the model would not be able to predict it well. So in a way, it has to, in order to fit that example, it has to memorize the label. And more formally, for dataset S, which will be n labeled example x I y I, and index I of an example in this data set, a learning algorithm which will denote by A will denote this memorization of an algorithm A at dataset S and index I as this difference between these two terms. The first term measures the sort of the accuracy, the prediction accuracy of the output hypothesis on the example itself when given the entire data set. And the reason we're looking at the probability here because most of the algorithms we're interested in are randomized. And the second term looks at the accuracy on that same example when the example is removed from the data set. Again, memorization is just the difference between these terms. And we'll informally say that an example is memorized, and this difference between these two probabilities is some large constant, say half or something. An important property of this definition is that it's directly relates to this so-called generalization gap, which is the difference between the true error on the unseen data and the empirical error. And I mean, this is the expression which says that in expectation over, for every distribution over the data, the expectation over the data set drawn from the data, the average memorization score is almost exactly equal to the, again, the expectation of the difference between the true error on the distribution and the error on the data set. This is the so-called generalization gap. And as I mentioned, so in particular, if one observes, it captures the intuition that if one observes these large generalization gaps, then a lot of data points need to be memorized by the learning algorithm according to this definition. And the question we'd like to address is this: why is it ubiquitous? Why do we see so much memorization in learning? And is it necessary? In addition to this theoretical sort of or maybe fundamental question, there are practical reasons to ask this question that come from privacy concerns. And we know that if we have a data set which contains some sensitive data, health data, or financial data, and so on and so forth, then outputting a model that memorizes many labels can pose privacy risks. And this is not a sort of a theoretical concern. We now have a long line of works on so-called black box membership inference attacks, in which it is possible to infer whether a point is in this data set and not just by observing the predictions of an algorithm. And we have known that we know that these techniques have been further strengthened more recently by Carlini and all to extract sensitive information from large language models. So from this point of view of privacy, the question is, can we sort of avoid memorization and still have high accuracy, the same accuracy as before? In terms of sort of, this is a question I'm not the first one to think about it. There are quite a bit of work has been inspired by these empirical observations that I've mentioned. Perhaps the biggest line of work is so-called understanding of generalization of interpolating methods. A method is called interpolating if it fits the training data perfectly. Sort of it is accurate on all the training data. And this line of work can be traced to a very old work of Carver and Hart, who looked at generalization of one nearest neighbor, which is the most sort of prototypical interpolating method. It fits all the examples exactly. And more recently have been quite a few works, which maybe at a high level can be summarized in the following way. Interpolation may be harmless in the sense that we know that many of these works demonstrate that interpolating algorithms can achieve almost the same generalization or even the same generalization as regular non-interpolating method. They are not necessarily worse or not much worse. However, from our point of view, they still do not address why question. Is the memorization actually necessary? And we also know that memorization happens without interpolation. In that example I just mentioned, the error was 9%. It was still not zero. It's not true interpolation. but there is a lot of memorization that was required to memorize the other 91% of examples. So far. That's the related work. So in this work, we'll give both theoretical and empirical evidence, so explanations for why memorization is necessary. But before going there, let me start with a bit of intuition. And it starts by looking at some examples taken from the CIFAR-10 dataset truck class, is an actual dataset with some images. And these are, I probably can't see those very well, but these are 4 examples of a truck from that dataset in the training set. And what's kind of special about those, and we have identified them using the technique I'll describe later, is that all of these examples would need to be memorized to be fit. So none of this, all of them are sufficiently different. Okay, they're also visually very different from other tracks that standard learning algorithm would not be able to predict them as trucks without actually observing these examples. And the question, so they need to be memorized in order to be fit. The question, is this useful or not? And again, using a technique I'll describe later, we will able to understand whether an example is useful or not. And specifically, we're able to see that this particular example in the training set was useful in predicting this example in the test set now as a truck. So if we were to remove this particular example from the training set, we would not be able to accurately predict on this truck in the test set. So it is a useful example. It is not an easy question, especially even for much. Yes, it's a kind of a dump. Yeah, it's a kind of it's a kind of dump truck with its thing raised. This does not seem to help predicting trucks, so that's not a useful truck to memorize. This turns to be useful to predict this example in the test set as a truck. Maybe you can see, but it also has some wheels. And finally, this looks like a stamp with a fire truck. Doesn't seem to be helpful in predicting other trucks as trucks. So you can see, as a whole, this is indeed the resolution that these learning algorithms work with. So it's hard for everybody. As you can see, as a whole, memorization of these 4 examples is useful. However, these are all 4 very atypical examples, very different from other trucks. So with only 5,000 examples of a truck to see, it might be impossible to know which one will turn out to be useful. And in order to be able to sort of gain the benefits of predicting the correct ones, it may be necessary to also memorize the incorrect ones, just because a priori you cannot tell which one of these unique examples is going to turn out to be useful. So that's at the high level. The question is, where do these hard and rare examples come from? And for this, the main intuition is that the natural data is not homogeneous like our favorite Gaussian distribution, but actually consists of many diverse subpopulations. For example, if we look at the example of birds, again, actual examples from CIFAR-10 datasets, they consist of hundreds of different bird species, taking it in different backgrounds, different magnifications, different angles. So, and many of these subpopulations are very, very different from each other. If all you know about the world is this 5,000 examples of birds. And because there are so many subpopulations, from some of these subpopulations, we will only observe just a single representative. There'll be just a single unique representative. And these will be from these unique representatives will typically come from subpopulations that have frequency on the order of 1/n. This is why you only observe a single example, but these are still useful subpopulation. Improving the accuracy by 1/n is useful for every example. At the same time, outliers, or things which are really extremely rare and useless, well, you'll also see them only once. And similarly, noisily labeled examples will also be something you'll see only once. So you might not be able to tell if these subpopulations are sufficiently distinct. You might be unable to tell between the examples from subpopulation with the frequency on the order of 1 over n, and outliers and random noise. So these are essentially indistinguishable, or maybe hard to tell apart. So so the question is whether we need to memorize these unique things, which are rare. Depends on the relative fraction of these unique or these subpopulations with relatively low frequencies. Are there many of those? Then we need to memorize. If there are few, then maybe we don't care. And the answer to this question, of course, depends on the distribution of the subpopulation frequencies in our population. And it has been informally mentioned by many practitioners. Know that natural distributions typically have so-called long tail. And what they mean informally is that these rare and infrequent things overall occupy a significant fraction of a distribution. So you cannot ignore that fraction of distribution. And beside this sort of folklore or empirical wisdom, there are some actual measurements in the literature. For example, Zhu and others have used additional annotations which are available in the SUN dataset, where they, for every image they have, in addition to its class, they also have the visibility pattern, which sort of side it is visible from. For example, this is the visibility for a class of bus, is the visibility pattern of being sort of up front. This is the back. This is somewhere abstracted, and similarly for a class of person. And then they plotted for these different visibility patterns their relative frequency. And this is a plot on a log-log scale of sort of frequency versus sort of in descending order. And if you can, as you can see in this log-log scale, this frequency has sort of a negative -1 slope, roughly, and that coincidentally corresponds to the famous zip distribution, in which the frequency of the kth most frequent element is proportional to 1 over k. It's famously followed by words frequencies in many languages. And what's important about this distribution is that if we look, if it has enough sort of elements, more than the number of elements is more than n, then the relative weight of all the frequencies between 1 over, which are roughly on the order of 1 over n, is at least 1 over log t. So it's a non-trivial fraction of the distribution has this relatively low frequency. Yeah, that's exactly what I was saying. So this long tail, the frequency of this type will occupy a significant fraction of the distribution. So we cannot ignore those. So that's the intuition. The natural distribution have this tail. And the important things in this, rare things in this tail are indistinguishable from hard atypical example. Yes, Alan.
Why not care about things that have weight much less than 1 over n, like 1 over n squared?
Because
also
yes, let's say you yeah, right, good question. So let's say you have a population of 1 over n squared, then even if you have a single representative from each of those subpopulations, you'll have subpopulations and subpopulations like this at most. And the total weight of the subpopulations, which will be represented by such example, will be 1 over n.
See, it's not going to affect your accuracy.
Yeah, it's not basically the question. Yes, the things which are on the order of n, if for every example you're gaining on the order of 1 over n, then the total fraction of these examples will roughly correspond to the total gain up to a conversion to a total gain in the accuracy, final accuracy. So we care specifically about those. So that's a completely sort of high-level intuition. Let me show that this can be captured relatively easily by a theoretical model of learning, a very general one, on one hand, but very much simplified on the other hand, just to make sure we can capture this very simple phenomenon. Or not so simple, but this specific phenomenon. And in this basic model, we'll have a discrete domain, capital X, of size t, and set of labels y, where t will be the number of subpopulation. In a more general model, and in a paper you can find a general model, each of those discrete elements will actually represent an entire subpopulation. But here in this simple one is just a single element, indivisible one. And we'll define a learning problem by a meta distribution over data distributions phi. Meta distribution phi, typically we think we're more used to these worst case learning models, but representing a learning using problem using a meta distribution is much more natural if you want to capture some prior information that you have about the data distribution. You know something about it. And the goal will be the usual one. A goal of learning will be to minimize the true error, but now the true error will be measured not in the worst case, but in expectation over data distribution P, sampled from this meta distribution phi, and of course the data set sampled IID from this data distribution, and the hypothesis output by the learning algorithms. So this is the goal is to minimize this average error on a meta distribution phi by an algorithm A. So now in our model, the goal is to capture that we know something about the distribution. The distribution of the frequency has to be some kind of long tail distribution, and specifically we'll express it using some kind of prior pi, which is just t different frequency. You can think of it as just also a distribution over frequency. We'll assume that the frequencies of elements themselves have a distribution, like a zip distribution. You can think of it as being specified just using just t different frequencies, the entire distribution. And how will we define a learning problem with a prior like this? Basically, we'll assume that aside from knowing that the frequency follow this prior, we don't know anything about this, about the actual frequencies of the elements. Specifically for each x in the domain x, we'll pick randomly and independently a frequency p of that element from among these t different frequencies from our prior. And then because we want the distribution, in the end, we'll renormalize everything to be 1. And independence makes the analysis much easier. You can also think of it as just effectively just permuting randomly these frequencies and assigning, but independently, again, analysis becomes easier without much other changes. So now this is the way we'll define sort of the distribution of our domain by picking these frequencies of a certain shape randomly. We'll also assume that there is some kind of distribution f over labeling functions, over functions that we're learning. Here we could as well assume, instead of a distribution, we could have taken the worst case notion, but it doesn't matter. We'll stick for simplicity with also a distribution over labeling function. And our meta problem phi for prior over frequencies and say prior over labeling functions will look as follows. We'll pick the distribution over domain according to this process that I've described, where frequencies are picked randomly, and we'll pick a random labeling function from this distribution over labeling functions, and that defines a problem distribution P. So for this model of learning in this generality, we prove the following theorem, which basically states that if you do not fit examples that occur once from these discrete domains, you will be suboptimal. And more formally, it says this: the expected error. This is the notion that we're trying to minimize over, again, choice of problem, data set, and hypothesis, is at least the optimum over all algorithms. This is the best achievable information theoretically, or by any algorithm, plus this term, which has this tau I'll explain. And this is the expected error. Okay, so this is the minimum. This is the number of examples that occur once in the data set S, but the algorithm doesn't fit. So suboptimality is lower bounded by the number of examples you don't fit. Multiply, again, the expectation of this number times this conversion factor tau, which is the price of not fitting the examples. And what's important about this tau is know its exact expression. It depends only on the frequency prior pi and the data set n, the data set size n, sort of the sample size. And what's not hard to show about this expression is that for all priors pi and n, tau is roughly the weight, asymptotically equal to the weight of this in this regime. All the frequencies which are the order of between, say, 1/2n and 2/n. This. Yes.
Sorry, what is? Oh, I'm sorry. What does fit mean compared to memorization?
Fit is just predicting when accurately an example in the data set. And memorization is required to fit correctly something in the data set when you cannot predict it otherwise, when it's a hard example. And we'll connect it in the next slide. We'll connect these two notions. Yes. So
Is there a second question over here?
So as I mentioned, this tau is basically determined by the this weight in the prior of these low frequency, significant but low frequency elements. And for example, as I mentioned, for zip distribution, this tau would be roughly 1/n log t, which again will imply a relatively significant price for not fitting each of the examples. Let me just very briefly mention two things about this result. So we haven't used it, it's completely independent of the function class f. It doesn't depend on the learning problem. It just says you have to fit if you want to if you want to be accurate. And it also, so far this problem, everything was, all the labels were perfect. They basically, this is no classification noise scenario, but it extends to the situation with the label noise as long as sort of the label you observe is most likely to be correct, the most likely one to be correct. So this is what's about fitting. Let's connect it to memorization. Just to recall very briefly, this definition of memorization is the difference between the predicting sort of fitting the example and predicting on it without observing it. So now predicting an example without observing it is exactly the true accuracy of the algorithm. So if the problem is hard, the true accuracy has to be relatively not too high. So there are many examples which you cannot predict well. So in order to fit those, you will have to memorize those. So if your problem is sufficiently hard, not a trivial problem. If your problem is easy, you don't need to memorize. Maybe that's one way to think about it. But if it's not too easy, you will not be able to just guess everything. So you'll need to memorize in order to fit. And we know that fitting is important. Yeah, so that's the all that I wanted to say.
Sorry.
Yes.
Sorry, I understand. So like, sorry. Thank you. So if I understand you correctly, you say that rare examples are very important to memorize because when they appear in a testing phase, the only way to correctly label them is to have memorized them.
Right. Basically, maybe what I have to say is that all rare examples, some of them will be useful, some might be complete outliers. All rare examples are important to memorize because you cannot distinguish between those two.
But like, you don't say that memorizing rare examples will help me predict other rare examples.
No, in fact, kind of in this model, I typically assume that they are sufficiently distinct in any way. The problem is they're all also distinct from other ones that you know about, so you have to memorize and everything. Yeah, maybe that's something, the point I should emphasize here is that we're showing that it's important to memorize the price, the cost of memorization is for all things you don't fit, even if it turned in actuality, that example is some kind of outlier with zero frequency or like close to 1/n squared frequency.
To my last question, isn't the difference between those two interpretations almost nothing? Like the difference between you have to memorize all the rare examples, even if they're outliers, versus all the rare examples, but only the non-outliers. The outliers, like back to my last question. The outliers are the things that happen with probability much, much less than 1/n.
Mhm.
So you're expecting to see very few of them. So,
No, not true.
so what am I misunderstanding?
Not true. Half of the population could come from frequencies which are on the order of 1/n squared. The overall fraction of of populations which are very rare, complete outliers, could be very large. You just can't. The point is, with those you can't do anything anyway. It doesn't matter. You won't be able to predict on those well because you will observe only a very small fraction of all those of things which are 1/n squared. The point of this model is that you will still need to memorize them all, because there might be also a fraction of a distribution. Imagine maybe
In my data set, I only have
Very few of them. In my
yes.
data set, I
No,
only
no,
have
no.
very
You will
few
have
of
a
them.
lot of them. Imagine a data distribution which is as follows. It has a bunch of subpopulations which are of the frequency 1/n, not a bunch of basically n/2. So half of the entire population has subpopulations with frequency 1/n, and the other half is subpopulation with frequency 1/n squared. Right. So in your data set, when you sample, you will see half from each of those, and you need to memorize everything, even though half is actually useless. And the difference between that's where the interesting parts comes from is that's where this generalization gap that's why the generalization gap will be large. You will actually only be able to predict well, let's say this 1/2 of the data set, but your training accuracy is 100. So you're 100%, and that's necessary. Anyway, in the interest of time, of which I don't have too much, let me go to empirical validation, which is a little more easier and fun. So the goal of this empirical validation is to both find these memorized examples and understand their influence. Why are they useful for learning, and what is their effect on the accuracy of the model on the training, on the test set. So again, this is the definition of memorization, and we would like to be able to estimate it, except it requires training a model on all the, while removing an example I. So in order to evaluate it on memorization for every example, we would need to train at least one model for every training example, which is prohibitively expensive even on small data set, and even if you're working for Google. Anyway, so we cannot estimate this value, but using a relatively simple trick, we have defined a proxy notion, which is very similar. And the difference is, instead of evaluating this memorization when you remove that single example from the entire data set, we measure the expectation of the same notion. When we, instead of measuring on the entire data set, we measure on a random subset of the data set, T, which is relatively large, let's say 70 or 80% of the data set. And we remove that example from that, just that subset. And the interesting part is that now, to evaluate this proxy, which kind of feels roughly the same and behaves very much, I believe, the same. Now, to evaluate it on all models, you basically need to only estimate measure all of one models. And that's just some simple linearity of expectation type of analysis. It's not so important for this talk, but it's a nice estimator, very nice proxy for some, and as you'll see, measure something very meaningful. So these are some examples of measuring this memorization score for the class of bobsled in ImageNet. And these are, just to be clear, not cherry-picked. We have a website with a lot more images, and just this is pretty much like the first one that came. This is high memorization estimates of the class bobsled. Some of them you could see aren't really bobsleds. Other are very unique images of actually a bobsled. I believe that's some kind of view of a bobsled. The other ones are, this is also a view of a bobsled. And these are low memorization. These are things which have pretty much 0 score. They're very easy. They don't require memorizing to be fit. So it seems to be doing the right thing, this estimator. Now, the next question is, and our hypothesis is that the reason why these are memorized is that they help predicting examples from the same subpopulation in the test set. And the question is, how can we confirm this? And for this purpose, we have defined this notion of influence, which is an influence of a example I in the training data set on the prediction at the example XY. Any example XY is just the difference in the accuracy on that pair XY when the example I is in the entire data set, and when the example is excluded from this, it's just the effect of that single example on the prediction accuracy at this pair XY. So we can now discuss the effects of training examples on predictions. We would like to estimate those influences. We cannot do it directly for the same reason. So we use just the same trick. We now define it, the same notion, just with respect to expectation of a random subset T, which is sufficiently large. And now we can run it again. It's not so cheap. It still requires training thousands of models, but doable. So this is just a bit of a distribution of what we observe is by measuring this, that we find many pairs where a single example has an influence of just a prediction accuracy on another in a training set, has a large effect on the training accuracy on example in a test set. And this is the specific influence is there from 0.2 to 0.6. And overall, if you look at the values above 0.2, you get, or maybe 0.15, you get more than 3% of the ImageNet test set is affected by these kind of very large influences. So the overall effect is large, but it may be even more interesting is to look at actual examples of these high influence. And these are, again, from ImageNet. This is the training example, which has the largest effect on some test example and this is the class, the specific one. It's maybe not so obvious, but these are all kind of very unusual example, relatively unusual and very similar to each other. That's why they seem to memorize Crane. That's one, and there are similar things from a smaller CFAR 100 data set. Also not so easy to see, but they're almost clearly very similar. We also easily find lots of duplicate in some of these data sets using these techniques, but that's a separate property of these algorithms. And these are the specific influence values, memorization values. Doesn't matter. That's sort of the rough some summary, and there are many more examples online if you like to browse those. Now let me discuss a little bit the implications of these results. And the first one is for differential privacy, because we can very directly relate the notion of memorization to differential privacy. And again, this is the definition of memorization, and it looks at the difference in predictions on some example. When you have an example and you remove the example, and if, I guess you just saw a couple of talks about differential privacy, you will realize that differential privacy relates these two quantities directly. And specifically, we almost immediately obtain that the accuracy on the example when you observe it is upper bounded by e to the epsilon times the accuracy on the example when you cannot observe it, plus this delta for an epsilon delta, any epsilon delta differential privacy, which implies that memorization score for any example is upper bounded. Basically, differential privacy limits your ability to memorize directly for this particular notion of label memorization. And now, because it limits this quantity, we know that we can, using the theorem, the type of the theorems that I've mentioned, it will directly imply that for these long tail distributions, differentially private algorithms cannot be as accurate, do have to pay some price relative to non-differentially private algorithms. Basically, they require more data to achieve the same accuracy, roughly, which is not in any way unexpected. But this kind of shows it formally beyond sort of, there are other reasons we know there are other problems, but this is a somewhat different type of phenomenon from what people have known in terms of the costs of differential practice. The other implication that I would like to mention is the so-called disparate effects. And there have been several works that have observed the following phenomenon. The first one is by Vitaly and Feldman. They observed that if you train a differentially private model on a population which has different subgroups, in particular differently sized subgroup in their case, and one happens to be lighter skin, the other is darker skin image set, then when you train with differential privacy, you experience a drop in accuracy. And this drop in accuracy seems to be larger for this sort of less well-represented group. So not only both groups experience a drop, but the drop is larger. So, and this they refer to this as disparate effect of a certain technique on different subgroups in the algorithm. And there's a very similar set of results from work by Hooker and others who look at effects of compression techniques where you try to reduce the size of the model that you have produced, for example, by throwing away all the small weights, doing some kind of quantization, anything you want to do to make the model smaller. That also naturally limits, when you try to compress the model, it limits how well it can memorize the data. And what they observe in this context, okay, this is really unreadable, but what they look at is the drop in accuracy as a function of different classes, and they see the different classes in the data set experience very different drops in accuracy. So it's not, the overall drop in accuracy is not distributed kind of uniformly. It depends very much on the class. So it's also, again, a disparate effect on different subpopulation or subgroups in the data set. And although this is just, there's nothing special, it's just car mirrors and peacocks and stuff like this. So both of these techniques naturally restrict the memorization, and the results in this work show that restricting memorization will cause suboptimality. And they also show that this suboptimality depends on on three different factors. This cost of non-memorization on accuracy depends on first on sample size, which again, if you have a smaller group, typically the overall weight of these low frequency elements will be higher. So the cost of non-memorizing will be higher. It will depend on subpopulation structure. It will depend on this prior frequencies that I've described. Basically, the more diverse in a way you have the population, the more likely that the fraction of these low frequency elements which are important is larger. So the cost of non-memorizing is higher. And finally, if the problem is if the problem is hard to predict, is typically, it also increases the overall value of this suboptimality, because everything is multiplied by this hardness to predict. So if, for example, your problem is the problem on a subgroup is harder, on one subgroup is harder than it is on the other, for example, you haven't collected the right features, or your data on that subgroup is worse, then again, the drop will be higher because it will be multiplied by a bigger value will be multiplied. Maybe it won't be higher in relative terms, but it will be higher in absolute terms, and that's what's being observed. So basically, this sort of view, this understanding in my mind explains why we see these disparate effects. So that's all. Let me just briefly mention some conclusions. I try to convince you that label memorization is necessary for optimal generalization on long-tailed data, which is the natural kind of data. This is not algorithm specific in any way. This is just we started looking at this because of deep learning, but it applies to all algorithms. It is possible to capture these things theoretically, although I believe more work is needed to sort of incorporate, to make a sort of a more general learning theory model out of it. And as I mentioned, it has interesting implications to effect on to differentially private learning, and also these disparate effects. In terms of, if you're interested in learning more, the theoretical part of this paper has appeared in Stock 2 years ago, experimental part in Europe's, and the resulting experiments can be found on this website. And we also include all the scores that you have computed so that you don't have to also burn more icebergs if you want to play. And a few people have already made some good use of this data. In terms of future work, I do hope it will inspire sort of more work on more faithful models of learning, and that sort of allow us to models in which theory more closely corresponds to observations, empirical observations. And the second line for future work, of which of these already a couple, is looking at other applications of these estimators of memorization score, and sort of to gain insights into deep learning more broadly. Thank you very much.
Thank you, Vitaly. I will like abuse my power as chair to ask a vague and leading question. So it seems like this work says in a pretty strong sense, you can't avoid memorization if you're doing learning in complex environments, like you're going to memorize stuff. And I'm thinking about sort of like legal requirements of privacy, and most of our laws don't cover machine learned models, but it seems like your work says these machine learned models sort of almost like information theoretically must memorize individual points. So like, how do you interpret these two things of the kind of implications of your work onto these like legal privacy notions?
Thanks for the question. I think that maybe this is a little bit too strong of an interpretation of this. It shows that there is a cost to non-memorizing. It doesn't mean that you cannot learn without memorizing. It just means that if you really want to be the top of the benchmarks, you really want to beat everybody else, then you have to memorize. And the more data you have, the smaller the effect, the cost is. And in practice, especially if you're a company with lots of devices and lots of data, that effect could be essentially negligible. You can, I don't think it's impossible to reconcile privacy and accuracy. It's just that there is this cost. It will be more significant when you have less data. So yeah, maybe there are some interesting questions, especially when you consider disparate effects, because these things do affect more subpopulations which have even fewer data. And for these subpopulations, maybe there's an inherent trade-off between privacy and accuracy that they can achieve. That is maybe for the people of this workshop to discuss much more than for me. But I think overall, the message is not so bad that we cannot learn. It's just there are trade-offs, and they get better if you have lots of data.
Thank you. I'll now share the mic. Oh my gosh, so many. Let's hear from a voice we haven't heard before.
Hi, thank you for the great talk. So if we have subpopulations where we don't have sufficient data, is there any benefit to creating synthetic data, by perturbing and sort of learning from that, so we're not directly memorizing?
Good question. I think first of all, there are many different ways to improve, and in general, if you can improve your accuracy by perturbing data, creating some kind of synthetic data or these kind of doing some kind of data augmentation technique, you should be doing this. There's no harm, and maybe even more extensively if you have little data for some subgroup. What this work shows is there are some inherent limitations which no learning algorithm can resolve. It's just you just won't be able to tell between some rare things and others. So maybe the question, you should be doing what you're doing, but it's not that. But not all problems can be solved by data augmentation techniques.
So I guess I wanted to ask, so the work shows that label memorization is necessary. Is there a sense in which memorization is sufficient to have good error for these problems, or sort of like if you memorize and maybe satisfy some other simple property, then in this learning setting where you have these zips distributions, you'll have reasonable.
A good question. I certainly the work doesn't say anything, and there is much more to learning than memorization. And in a way, this work is about saying that memorization is important. It's not that the other things are unimportant. In fact, balancing capacity and kind of, and it could be important for some parts of the data. It's at least I don't think that there are any implications in this work that's enough. We do need to find good representations for data. It's just memorization. We know that just say nearest neighbor will not do well on a.
Even in these problems, even in this like theory model.
Okay, so for this theory model where you have a discrete set of just T points, yes, that's just memorization. There is nothing else you need because no, so even that is not accurate. If you, there is still a question, what do you assume about the learning, the function class? If you don't assume anything about the function class, let's say that all labels are independent, then it boils down to just memorizing because there is no relationship. But if there is some structure, you can still learn better if you exploit the structure of labels.
Okay, so I know there were more hands, but I think in the interest of time, let's save those questions for tea time, and let's thank Vitaly again for his.
Thank you.
So we have tea now upstairs on the second floor, and tea